All this is Dr. Mobeen Sayed from drbeen.com. Welcome to one more show. So the muscle aches and pains, fatigue, neurodegeneration, dementia, cognitive decline, joint pains, liver damage, renal damage, diabetes, and then the secondary damages, diabetic neuropathies, diabetic immune system dysregulations. Underneath all of those diseases is inflammation. And underneath the inflammation is some abnormality of, let's say, lipids, for example, omega-6, omega-3s, glycations of the systems that are going on, some epigenetic changes that have happened, some environmental factors, for example, pollutants and smoke and so on. So there is something underneath. Bad food, for example, fried foods, then that causes inflammation, and then inflammation then gives rise to the tissue damages and tissue dysfunction that gives rise to diabetes, cancers, and many other such diseases. One core function that occurs during the inflammation is the production of reactive oxygen species and reactive lipid species. Comparing them to each other, reactive lipid species are much more dangerous than reactive oxygen species, because once the reactive lipid species are formed, they will get into a chain reaction, and every burnt up or reactive species will damage the next one, which will then become reactive, and that would damage the next one. And this chain reaction continues until some antioxidant system comes in and stops that. Reactive oxygen species, on the other hand, are dangerous because it is the reactive oxygen species that starts the chain reaction of reactive lipid species. A reactive lipid species does not just become reactive by itself. It has to be hit by a reactive oxygen species, then the chain reaction starts. This is like a primer, reactive oxygen species being the matchstick, which then puts on the fire in a bomb making factory, and then the whole factory goes off. So the question is, how does this happen? This is the core foundational aspect, one of the core foundational aspect of the inflammation. There is the tangled proteins, that is another, epigenetic changes are other, glycation products are other, and so there are many factors. So today we'll discuss what are reactive oxygen species, how are they formed, and then how do they create reactive lipid species, and how do the reactive lipid species go in a chain reaction. Before this video today, I discussed another video that could have come after this one, and that is that when you are taking antioxidants, it is important to take antioxidants of the category of water solubility, so they can take care of the reactive oxygen species, and antioxidants that can be going into the lipid zones of the cell and take care of the reactive lipid species. So a lipid soluble antioxidant, for example, vitamin E, and a water soluble antioxidant, for example, vitamin C, have to be provided together so they can partner for the two zones. Plus vitamin C heals vitamin E. So I did that discussion separately. Now I'm going to go into the mechanistic discussion of this. So if you're not interested in mechanism of how reactive oxygen species are formed, then this is not a video for you. You can just watch the previous one where I discussed the components, the supplements, or these can be found in foods as well. Okay, so let's start. So blank canvas here. We'll start with this one. Imagine that we have an oxygen. Oxygen is, let's say these are the two oxygen atoms that are near each other. And oxygen atoms, I'm going to go in tiny bit of a detail on chemical detail, which would be necessary, but not necessary for you to remember it. In the outer shell of the oxygen, there are 8 electrons each. I just made them like pairs, but there are 8 electrons each. This is a stable oxygen molecule. It becomes reactive when an extra electron becomes part of this molecule. Each oxygen atom has 8 electrons, 8, and then, so really I made it a little wrong. For the 8 one, there are 2 in the first valency, and then there are 6 outside, something like that. Anyways, there are a total of 16. As you can tell, I'm not fully up with this one. The important thing is that there is this extra electron that is given. So the first question that we have to answer is, where did this extra electron come from to make this oxygen reactive? This is a reactive oxygen species. This is a ROS. This is a superoxide anion. Superoxide anion, or a reactive oxygen species. This is carrying a reactive electron which is extra with this oxygen, and this oxygen now, reactive oxygen now, is going to look for things or other molecules to give this electron to them, to impart this energy into them. So it is running around this oxygen with a loaded gun, and whatever comes in front of it, it's going to fire on it. What is that fire? It's going to try to give this electron to them. Okay, so the first question to answer is, where did this get formed? In our cell, there are many areas where reactive oxygen species can be formed. For example, NADPH metabolic system, FADH metabolic system, Krebs cycle can make it. But the most important area where it is formed is mitochondria. So inside the mitochondria, so imagine that this is a mitochondria. Inside the mitochondria, there is a double-layered membrane on which there are electron transport chains. Electron transport chains, or ETC, is comprised of 4 components. We just simply call them complex 1, 2, 3, and 4. Then they are combined with another protein called ATP synthase, which is a mechanical motor with a huge number of revolutions per minute, and that makes energy, or ATP. We're not concerned with how the electron transport chain works. But important thing to consider here is that when the electron transport chain is running, what does it have? It has the nutrients from the food that you have eaten in the form of NADPH. That is one molecule that contains the energy that you have eaten from your fuels like carbohydrates, lipids, proteins. And then there is another molecule called FADH. These 2 molecules are carrying the energy that was present in the food you ate. That energy has arrived here in the mitochondria. Similarly, the oxygen that you breathed, that oxygen is also present here. So there's a lot of oxygen here. So these guys, these oxygens, are present here as well. Why? Because as we make energy, ATP, from the fuels you have eaten, we need oxygen to make the ending of the fuel is carbon dioxide and water. This is why the food that you have eaten, if somebody asks you, where did that food go? The normal answer is that some part of this went out in stools. Good, that is correct. Then the second most common answer that I've heard is the heat that we produce is the food that we ate. That is not entirely correct. Of course, that is coming from the food that we ate. That heat is actually produced by these motors that are running, plus various other chemical actions that are happening. But most importantly, that energy is actually converted to carbon dioxide and water. So the air that you are breathing out is actually the food that you ate that has become carbon dioxide, and the pee that you're doing, that has the water from the food that you ate. I'm simplifying this. There are many other possibilities. But anyways, this oxygen is present here. Now what happens is, through this electron transport chain, as the name is, electron transport chain, the electrons, which are high energy packets, the energy that you ate, these electrons will be moved through this chain, and they will move from higher valency molecules or atoms to the lower valency molecules. What does that mean? When we have an atom, so let's say this is an atom. Atom has these valency shells around this. So the electrons are running around the atom. If an electron has more energy, so we have to agree first that electron can actually have more energy and they can have less energy. Electron can absorb energy and become higher energy state or excited state, or they can lose energy and go to a more less energy state or stable state. So the electrons that are running more closely or circling the atom in the atom more closely to the nucleus of the atom, they are low energy electron. If you give this electron some more energy, it would jump from this with the excitation with more energy, and it would try to escape, and it cannot escape, but it gets trapped at a farther distance and start revolving in that area. Then you can take the energy away from this electron, and this electron would then go back into a more stable state. So the basic idea is that electron can take energy and give energy. So here, imagine that this electron is present at a higher energy state. If you transfer this electron to another atom where it is now asked to live in a lower energy state area, then it would release the remaining energy. This is what electron transport chain does in a simpler way, that it runs the electron through it, and it continues to move the electron from higher energy state to lower energy state, releasing the energy in that process. However, these electrons that are moving through these molecules, some of them escape, especially from the complex 1 and complex 3. They start escaping. 2 to 5% of the energy that you have eaten will become converted to reactive oxygen species. How? The electron would escape from here, and guess what is nearby? Oxygen. So that electron would get loaded on the oxygen. And all of a sudden, what do we have? We have a reactive oxygen species. 2 to 5% is normal. Our antioxidant system in the cell, for example, NADPH oxidase, superoxide dismutase, catalase, vitamin C, vitamin E, glutathione, they can actually neutralize this, and we are not damaged by them. However, when our cell is either not performing well, or when we have eaten enough that we have a lot of reactive oxygen species produced, or when the cell mitochondria are damaged, or for example, let's say when we have less CoQ10, which is an important vehicle here within the electron transport chain, then the electrons, more electron than 2 to 5%, will be released. And as they are released, they would make more oxygens reactive. Now these oxygens, so if I go here and make a cell, let's say that in this cell, this was the mitochondria that we were just discussing. These reactive oxygen that are formed will get out of this mitochondria. They can actually stay within the mitochondria and damage the mitochondria itself. And they can get out of the mitochondria, and guess where are they? These are now in the cytosol. This is the water soluble environment of the cell. Here, these loaded oxygen species will look for any molecule to come in their way, and they can just give that extra electron, that extra burst of energy to that molecule. So imagine there is an innocent little enzyme that is sitting here doing its function. Let's say it is a phospholipase A2 enzyme, or let's say it is some other enzyme working with some energy system. And this enzyme, just by accident, was in the way of this reactive oxygen species that was running around. That reactive oxygen species is going to impart that electron to this enzyme, and then the oxygen would become normal. It has given up its energy to someone else. Now, the energy that is received by this enzyme will cause this enzyme to bend in its shape. Why? So if I make that enzyme over here, so let's say this is that enzyme. I'm just going to make a rough diagram of that enzyme structure. Let's say this is the structure of the enzyme. No enzyme has this structure. So this is just me creating an illustration. So imagine that this enzyme has this structure. There are two boxes that are connected with each other through various pillars, and there is an empty space between them. This is an enzyme. Here you come with a burst of energy that is imparted to this bond between them. And imagine that all of a sudden, one of these pillars is broken down. What will happen is, when that is broken down, this system is now going to become D-shaped. So what happened here is that this one of the pillars collapsed and the enzyme has become D-shaped. This is called misfolded protein. When this protein is misfolded, there are three next steps for this protein to be repaired or recycled. The first step is that there is a protein called heat shock protein, or HSP, and you can activate these proteins either by misfolding the proteins as you're seeing here, or if when you go to sauna, they become activated. When you go to cold temperature, they become activated. When you do exercises, they become activated. Any stress on the cell can activate heat shock proteins. These, excuse me, these heat shock proteins will try to engulf this little damaged protein and try to provide it an environment where it can be repaired, it can regain its pillar, and that electron can dissipate away and the protein can become restored to the normal state. And many proteins do become restored. So that is the first one. You can call this as a little incubator for this baby broken protein to allow it to heal itself. The benefit of the heat shock protein is that it has various kind of enzymes and energies available for this protein to heal itself. Plus, it also protects this damaged protein from further bombardment by other reactive oxygen species, which will, every time a species would attack it, this protein would keep becoming malformed or D-shaped further. And we don't want that. The more D-shaped or misfolded it will become, the difficult it will be to repair this protein. So that is the first step. If this step allows the protein to become repaired, then this protein is allowed to come out of the heat shock protein and start doing its normal functions again. However, if for some reason the heat shock protein is not able to repair it, then what would happen is that the heat shock protein would say, you know what, I am not working with you, I cannot help you, you are now in a need to be recycled. So it will tag this broken protein, not broken, but misfolded protein, with another set of proteins that are called ubiquitins, which is a flag on this system to say, please, working crew members, repair people, the doctors of the cell, please come and recycle it. So ubiquitination system will occur. That is the second step that would occur. And ubiquitination system is that there are other chaperone proteins that will pick up this protein. These are called caspases. You know, Casper the friendly ghost, caspases. Caspases, if I know the spelling, that will be awesome. The caspases will come up and they will pick up this protein and bring it to another molecular wood chipper. I learned this name yesterday, wood chipper, but this is actually endosome. Have you seen the wood chipper, how it works, that you put a tree or something in it and it just breaks it up into smaller pieces? So this misfolded protein will be brought into an endosome. It will be dragged to the endosome by chaperone proteins, and they would put this protein inside the endosome. Endosome will then in turn pick up this damaged protein and break it up into smaller pieces and release those pieces in the environment of the cell to be reused to make other proteins or make energy from. So this is the second possibility. Many times, if the protein has become too much D-shaped, imagine there are too many reactive oxygen species in the cell. We are too much inflamed, or we are eating things that are causing a lot of inflammation to us. Carbohydrates are notorious for doing that. So whatever it is, everybody has a different set of things that can trigger inflammation in them. So now imagine that this is the protein's shape. It is too misfolded. Now the ubiquitination system, even when it would try to ubiquitinate this, will say, you know what, we cannot work with this protein. We can't handle this one. So now what would happen is this protein will be left alone in the cellular environment to say, you are on your own and we can't do much to you anymore. And imagine that there are now going to be other proteins that are going to be of this folded or misfolded type as well, because they were also attacked by the reactive oxygen species. And now these misfolded proteins would start tangling with each other. And, dementias are one such um, outcome of these tangled misfolded protein. Chronic inflammation, when we are 50 plus, the cell in a chronic inflammatory state is because of these misfolded protein that have become tangled. And I would keep giving this disclaimer that it is not the only one pathway for inflammation. There are many reasons for inflammation other than misfolded proteins. So now these are made a tangle in the cell. This tangle can only be repaired by autophagy. There is there is no drug, there is no mechanism, there is no immune defense mechanism that can extend its hand inside a cell and clear out these misfolded proteins. There is nothing except whatever can trigger autophagy. Autophagy is a process in which there will be a small structure that would be built near the misfolded proteins tangles, and this structure would take a bite out of this and try to clear this out. So I believe that we should, especially with the kind of diet and lifestyle we have nowadays, we should do intermittent fasting at least once every week so that we can allow these tangles to be recycled. So what happens is when autophagy starts, these autophagosomes can actually take a bite out of this tangle, and then they can help digest that with the help of the lysosomes. All those supplements and drugs that can trigger autophagy can help with that. For example, resveratrol, or for example, curcumin and quercetin and others, or all those things that can be mimicking fasting. For example, there are foods that are not really very full with the energy, but they are filling for our stomach. They would create a hunger mimicking environment, which would then trigger autophagy. Intermittent fasting is an excellent way. It's a cheap way. It actually saves you money, and then you become healthy as well. These would all trigger autophagy, and then these misfolded proteins can be recycled, and you are good with your cell. Now, the point was not really just to talk about the misfolded proteins. If I go back here, now we know that how a reactive oxygen species starts this whole cascade of the problem, which then needs to be solved, or if it is not solved, we get inflamed. But that is not the whole story. Now let's go to cell membrane. So let's say this is the cell membrane, which is a lipid bilayer. It's a fatty zone. And these membranes are present around the nucleus as well. They are present around the mitochondria, smooth endoplasmic reticulum, rough endoplasmic reticulum, Golgi apparatus, etc. They are present around every compartment of the cell, in the cell itself. When this reactive oxygen species, when this reactive oxygen species enters the lipid environment, what it does is the following. I have that diagram over here. So this is that lipid environment. This is the cell membrane. If you see there, the lipids are present in this structure. There is a phosphate on one end. Outer side and inner side is made up of phosphates. And then the sandwiched area is lipids. And if you see, I made some lipids that are bent. The lipids here are saturated lipids, and there are polyunsaturated fatty acids as well, or PUFA. PUFA. These bent ones are the polyunsaturated fatty acids. Polyunsaturated fatty acids are the fatty acids where the two carbon have a double bond with each other instead of single bond. And I should not have done this. So let's say like this, something 1, 2, whatever, 2. So 2 bonds are here, actually here and here. So in the saturated ones, we do not have double bonds. These double bonds in the carbons between the carbons are the area where reactive oxygen species attacks. These are weaker areas of the bonding. And when there are double bonds present in these carbons, that is where the carbon chain becomes bent. And this bending actually is good. Omega 3, omega 6, omega 9s, these produce bend in the lipid. And that is good because bending of this lipid molecule makes the lipid molecule push the other lipid molecules away from it. So imagine if 100 people are standing together and every one of them has a leg kind of little stuck out. That would make the other person stand a little at distance from them. And that distance is very important because that distance allows the fluidity of the membrane. And our cell membranes have to be fluid to be able to function correctly. So these bent lipids, the polyunsaturated fatty acids, are necessary for the cellular membrane fluidity. These get attacked by the oxygen. So now let's say we take one of them and put that over here. This one is one polyunsaturated lipid here, and it got attacked by a reactive oxygen species. What happens is that reactive oxygen species would extract a hydrogen from it, and now this thing will become reactive. This lipid has now become reactive. So like a reactive oxygen species, which will, give up its electron and be done and become non-reactive, lipids don't do it. You bother them, they'll become infinitely upset. How would that happen? Once the hydrogen is taken out, this lipid, which is reactive, will now combine with oxygen and will become a reactive oxygenated lipid, which would then attack another lipid and extract its hydrogen. And that would now become reactive, and that would go and attack another one and extract that lipid's hydrogen and make that reactive, and that would attack another one. And this chain reaction will not stop until there is an antioxidant that would come and stop this. And which kind of antioxidant that has to be? That has to be a lipid-soluble antioxidant, for example, vitamin E, or alpha-lipoic acid, or quercetin, or CoQ10. It has to be lipid-soluble antioxidant. A water-soluble antioxidant, for example, glutathione, or for example, NSE, or for example, vitamin C, will not work here. So this chain reaction is more dangerous. So lipid peroxidation or reactive lipid species are more dangerous than reactive oxygen species, because oxygen species would be a one-time fire and done. But reactive lipid species are like dominoes that if you react to make one reactive, it is just going to keep breaking the other ones as well. Alexander said a very, very interesting comment. He said, imagine being infinitely upset. That is what happens. These lipids become infinitely upset and they just keep tipping over the other lipids as well. This cell is in trouble. One, it would possibly have its cell membrane broken up or have little gaps in the cell membrane. These lipids that have become reactive can actually leave the cell membrane and they would go and react other places, but now the cell membrane itself is damaged. They can make the cell membrane fluidity less, and the lesser cell membrane fluidity actually causes the cell functional disruption, which also causes inflammation. So this is the mechanism of production of reactive oxygen species and reactive lipid species. If you would like to read more about the reactive lipid species, you can Google lipid peroxidation. This mechanism is called, this process is called lipid peroxidation, and reactive oxygen species is reactive oxygen species. So this is the discussion. I hope that it made sense. If you now watch the video before this, I have talked about the pairs of antioxidants that should be taken if there is inflammation suspected with your doctor's advice. And these pairs have to be water soluble plus lipid soluble. Just taking vitamin C, which is water soluble, is not sufficient. Just taking vitamin E, which is lipid soluble, is not sufficient. So this is the discussion. Just one more point, that lipid peroxidation, does not start until there is a reactive oxygen species present. Reactive oxygen species will go and cause the first lipid to become reactive. And then they would become self-independent to keep propagating that damage between them, the lipids. So that is the discussion. Thank you very much. I hope it made sense. Please like, subscribe, and share. That is how you can help me back. There are links in the video as well. If you would like to support this work, you can become part of Patrons or Substack. And then you can actually become part of Drbeen as well, where there are CME-based videos available too. So with this, thank you very much. And I would see you tomorrow on Cool Beans Cafe Live channel, and we'll do chit chat. This time we'll actually do real chit chat and not teaching. We'll just talk. And Bob, you're very welcome. Alexander, you're very welcome. Paul, very welcome. Rebecca, you're very welcome. Carrie says, how long would you think a fast should be done each week? How many hours? Fast. So very good question. I have done some videos about fasting as well, but let's say you want to start with the fasting. The first thing to do is to remove snacks between the meals. So sterilize those times. That is one. The second thing to do is to maybe pull the dinner earlier or push the breakfast later. And so as you start compressing them, there is more hunger time, there is more fasting time, and eventually skip one meal. So imagine the best is if you look at Dr. Jason Fung's practice, he would say one dinner only, and then the next day skip the breakfast. So you go from dinner to the lunch, and that day you were hungry from dinner till the dinner. So you could do that, or you could start from the dinner on one day, on the second day, lunch and dinner, or breakfast and dinner, and then skip the dinner, breakfast and lunch, and skip the dinner again. But you could start in a more controlled and easy way. For women, it is important that when they do intermittent fasting, it is possible that their hormonal levels might change. Because of that, they may have their periods disrupted as well. So just be there are methods for doing that during the ovulation, what should be done, during the luteal phase, what should be done, during the periods, what should be done. And so there are many helpful PDFs available for them. But once a week, intermittent fasting, if we are above 50, that should be part of our routine. And that is one. And secondly, every so often, a help with antioxidants is going to be marvelous. If there are these lipid peroxidations happening, at least the lipid-based antioxidants would go and break that cycle. We need the water-based antioxidant to then regenerate the lipid-based antioxidant. So vitamin C plus vitamin E are important to take together, or other combinations of these, which I discussed in the previous talk. So with this, thank you very much. Like, subscribe, and share, and become member of Patrons or Drbeen as well. And I would see you tomorrow. Bye for now.